Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 31, and today we are going to talk about different theories of failure. So, let us think of an arbitrary body which could be clamped at some points on the surface, and then it may be subjected to traction on other parts of the surface. And as we load the traction, which means as we increase the traction value, the body is going to deform more and more, right. And at one point the body can actually fail, right. So, that failure could be either in terms of having a crack in the body or in terms of the body getting deformed a lot, which we will see later on, we call it as yielding. Okay. So, it can fail either due to a crack developing in it or due to yielding. All right. Now, the question is, why is the body failing? So, at a point in the body we have a stress matrix. So, why is the body failing? Is it because one of the stress components have reached a critical value? Is it because the principal stress component at that point reached a critical value? See, different points in the body will have different state of stress, and the failure will usually initiate from one point in the body. The failure does not happen at all the points together. So, it initiates from one point. So, why did the failure start from that particular point? Is it because the principal stress at that point reached some critical value? Is it because the maximum shear stress at that point reached a critical value, or it is not related to stress, but to strain? Is it because the maximum normal strain reached a critical value, or the maximum shear strain reached a critical value, or is it neither stress nor strain and it is somehow related to energy? Is it that the energy stored at that point has reached a critical value? So, based on these various points, different theories of failures have been developed. So, let us list them together. So, the first one is maximum principal stress theory, in which case we look for the largest principal stress value, okay? And if it reaches a critical limit, then the body can fail. Then the next one is maximum shear stress theory, then the next one is max normal strain theory. We also have max shear strain theory, then we have distortional energy theory, and notice we are not talking about the full elastic energy at the point, we are only talking of the distortional part of the energy, and we do not say max distortional energy, because we have single value of energy at a point. Principal stress we have got 3 of them, therefore, we talk of max principal stress. Shear stress on different planes we have different shear stress, so we talk of max shear stress. likewise for max normal strain or max shear strain, but for energy at a point we have got a single value for energy. So, we do not talk of max distortional energy, it is just the distortional energy theory. And finally, what is called octahedral shear stress theory. And you will see that the last two theories are actually related. So, to obtain the critical limit of failure, usually we do simple test, for example, simple tensile test or torsion test. So, for tension test we can think of a bar and we can pull it from both the ends. Okay. Suppose this is one axis and we are applying sigma 1 and sigma 2 and sigma 3 are 0. So, it is a simple tension test and we keep on loading sigma 1 and then we see that at one point when the sigma 1 value reaches a critical value, the body has failed. So, that will give me the information of critical value for sigma 1. Now, suppose that the body is such that it is obeying the max principal stress theory. So, in that case, since it is a simple tension test, what is the state of stress here? It is going to be sigma 1 0 0 0 0 0 0 0 0. So, all the stress components would be 0, and when you find out the principal stress components from here, then lambda 1 is sigma 1 and lambda 2, lambda 3 are both 0. So, what is the max principal stress? That is simply sigma 1. So, this means if it is failing due to max principal stress theory, then sigma 1 should be less than equal to the critical value of failure, okay, where sigma y is the critical value. Of principal stress. Okay. So, for this tension test, sigma 1 is also the max principal stress, but for a general deformation or for a general loading of the body, the max principal stress will be lambda 1, right. The tension test here simply gives me the critical limit, which is sigma y in this case. So, as you keep on increasing sigma 1, at one point we see that it has failed. So, the point at which it failed, that gives me the critical value sigma y, and then once we have found out sigma y, we can apply general loading to the body, and then all that we have to see is that the max principal stress, which is lambda 1, that should be less than or equal to sigma y, right. So, for general loading, lambda 1, which is the max principal stress, and you have to find that, right. So, you will have a general stress matrix, find the eigenvalues and the max of it, that is lambda 1. So, this should be less than sigma y. Okay. But this theory has got limitation. This was not able to explain several things. For example, you take a a spherical ball and apply a lot of pressure to it. So, it was found that it can sustain lot of compressive load, but it does not sustain tensile load. So, if you only apply pressure to the spherical body, it is in the state of hydrostatic state, right. Then the state of stress is minus p minus p minus p. So, what is the maximum value of principal stress? That is simply minus p, and it is seen that you can keep on increasing the pressure and the body never fails. So, that means maximum principal stress theory is not working there, is not it. So, therefore, the mechanicians went ahead for another theory of failure. So, the second one is max shear stress theory. Okay. So, in this case again, to find out the critical value of shear stress at which the body is failing, what we can do is we again do our simple tension test. And we keep on increasing the value of sigma 1 okay. And then at a critical value the body would have failed, right. So, what is the state of stress? It is again sigma 1 1 0 0 0 0 0 0 0 0, and then what is the maximum shear stress corresponding to this state of stress? So, notice here the principal stresses here are sigma 1 1 0 0. So, what is the maximum shear stress? That is lambda 1 minus lambda 3 by 2. So, for this particular case tau max is simply sigma 1 1 by 2, correct. And then when the failure has happened, sigma 1 1 was equal to sigma y, right. So, what is the maximum shear stress limit? So, what is tau y, the limiting value of failure? So, that is simply sigma 1 1 at the limiting value, which would be sigma y divided by 2, correct. So, this is how you can extract the value of maximum shear stress. So, you see these are all material constants. So, once you have found out the value of max shear stress from a simple tension test, then you can again think of general loading scenario, and in that case you will have 3 values of principal stress components lambda 1, lambda 2, lambda 3, and then the maximum shear stress for that particular state of stress is lambda 1 minus lambda 3 divided by 2, is not it. So, all that we have to ensure is that lambda 1 minus lambda 3 divided by 2. So, this should be less than sigma y by 2. So, if at any point in the body lambda 1 minus lambda 3 by 2 is less than sigma y by 2, then the body will not fail due to maximum shear stress theory. Okay. And how did we get sigma y? That is from the simple tension test. You see, we can also obtain critical value of shear stress from torsion test. So, if you do torsion test, you will have your circular beam and you are going to apply torque at the two ends, right. So, it is going to twist. So, what is the state of stress at any point in the cylinder? So, for torsion we have seen that sigma matrix in cylindrical coordinate system has got everything 0 except for tau theta z. Okay, now corresponding to this state of stress, we can find out what is the max shear stress. So, to do that you can draw the Mohr circle, right, because you see that one of the axis is already a principal axis. So, when we do the Mohr circle, the sigma y y and sigma z z are both 0. So, the center of the circle is simply at the origin, and then we have tau theta z over here. So, we get a circle centered at the origin, and then we can see that this is also your tau max, right, the max value of shear stress. So, tau max is also equal to tau theta z. In the cross sectional plane, whatever is the value of shear stress, that is also the maximum value of shear stress. Okay. And you can find out what is the relation between the tau theta z and the torque applied. See, tau theta z, for example, is g times gamma theta z, and gamma theta z is equal to the twist in the beam into the radial coordinate small r. Okay. And then you know that twist is related to the torque by this formula, that torque is equal to g j times the twist, correct. So, if you substitute that back, we get tau theta z equal to g into t by g j into r. So, this implies your tau theta z is nothing but t into little r by j. Okay. So, in the cross section, tau theta z is also the value of maximum shear stress at that point, and then in the cross section, as you change the radius, tau theta z changes and it attains the highest value on the outer surface of the cylinder, okay, where the value of small r is maximum. Anyway, so when you do this torsion test, you are going to apply a torque, and at a critical value, let us say at t star, the body would have failed, right. So, that means your tau star theta z is simply t star into the outer radius big R by j. So, this is how you can extract the maximum shear stress of failure from the torsion test. And then you can think of any general loading scenario for an arbitrary body. So, at a point it will have an arbitrary state of stress, you find out what are the 3 principal stress components, and then lambda 1 minus lambda 3 by 2, that is going to give you maximum shear stress, right. And you have to then say that lambda 1 minus lambda 3 by 2 at any point in the body should then be less than tau star theta z, which is actually t star into big R by j, all right. So, that is the maximum shear stress theory. Similarly, we can think of maximum normal strain theory and max shear strain theory. Let us now have a look at distortional energy theory. Okay. Now, suppose that we have an arbitrary body, and then at any point in the body we have arbitrary state of stress. So, we will have 3 principal stress components, right. So, let us say the 3 principal stress components are sigma 1, sigma 2 and sigma 3. Which of course, you have to find out by solving the eigenvalue problem. They are the eigenvalues of sigma matrix. So, what will be then the strains if we know stress sigma 1, sigma 2, sigma 3, then in the coordinate system of principal stress, what will the strain matrix look like? So, since it does not have any shear stress, then there will not be any shear strain also, because shear stress and shear strain are related to each other, proportionally related. But then what will be epsilon 1, epsilon 2 and epsilon 3? So, you can use the 3D Hooke's law. Epsilon 1 is equal to 1 over E into sigma 1 minus nu times sigma 2 plus sigma 3, right. Likewise, for epsilon 2 and epsilon 3. Now, what is the total energy? What is the elastic energy at any point? The energy per unit volume. Okay. So, strain energy per unit volume we have seen that this is nothing but half of sigma I j into epsilon I j, and then in the coordinate system of principal stress, sigma I j has got only sigma 1, sigma 2, sigma 3. So, this is half of sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. Okay. And then we have epsilon 1, 2 and 3 in terms of sigma. So, when we plug it here, we get half of sigma 1 by E into sigma 1 minus nu times sigma 2 plus sigma 3 plus sigma 2 by E into dot 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 plus sigma 3 by E into dot dot dot, right. And finally, when we combine all of them together, we simply get 1 by 2 E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Okay. So, that is the total elastic energy per unit volume at a point. We have to extract the distortional part of energy from here. So, you can recall that we had decomposed the stress matrix into hydrostatic part and the distortional part, likewise for the strain matrix also, is not it. So, how much would be the volumetric energy? So, the volumetric energy, or we call it volumetric strain energy, which is responsible for change in volume, that is simply half of sigma volumetric into strain volumetric, okay. And sigma volumetric is trace of sigma matrix divided by 3. So, that is sigma 1 plus sigma 2 plus sigma 3 divided by 3 into strain volumetric, epsilon 1 plus epsilon 2 plus epsilon 3, the volumetric strain. So, when you add the 3 formulas here together, you get the volumetric strain, and that turns out to be 1 over E into sigma 1 plus sigma 2 plus sigma 3 minus 2 nu into sigma 1 plus sigma 2 plus sigma 3. Okay. So, finally, when you combine them, we get 1 over 6 E into sigma 1 plus sigma 2 plus sigma 3 into sigma 1 plus sigma 2 plus sigma 3 into 1 minus 2 nu. Okay. So, that is the volumetric stored energy. So, the distortional energy is then total energy minus the volumetric strain energy. Total energy minus volumetric strain energy. Okay. So, we simply have to subtract this equation 1 and equation 2. So, upon subtracting, we simply obtain 1 plus nu divided by 3 E into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. Okay. So, that is the total distortional energy, and when we do our simple tension test. So, in case of simple tension test, you only have sigma 1 1. So, sigma 1 is there, but sigma 2 and sigma 3 are both 0. So, what will be the distortional energy for the simple tension test? So, that is going to be equal to 1 plus nu over 3 E into sigma 1 1 square, is not it? So, when we do the tension test, we are going to load sigma 1 1 and then we will have a critical value at which the body will fail. So, if the body is failing due to distortional energy, then this should be less than 1 plus nu over 3 E into sigma 1 1 star whole square, right. So, this is only for simple tension test, but notice that simple tension test gives me the critical value of distortional energy, which is this number. So, for a general loading, the distortional energy is this entire expression. So, that means for a general loading, we should say that 1 plus nu divided by 3 E times sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. This should be less than 1 plus nu over 3 E into sigma 1 1 star square, and sigma 1 star is the critical value that you got from simple tensile test. So, this is the critical value from simple tension test. If we do torsion test, so for torsion test, the sigma matrix has got only tau theta z plus dollar 0 . So, if you draw the Mohr circle, we get a circle centered at the origin. So, that is your sigma 1 and this is your sigma 3 and sigma 2 is 0 in this case, right. And what is sigma 1 equal to? That is simply tau theta z star, right, because this is also the radius, and sigma 3 is equal to minus tau theta z star. Okay. So, how much is the distortional energy for the torsion test? So, you have to come back to this formula and plug in sigma 1 equal to tau theta z and sigma 3 equal to tau theta z, right. And when we work this out, we simply get 1 plus nu by 3 e into sigma 1, which is tau theta z star square, plus sigma 3 square, which is minus tau theta z star square, minus sigma 3 into sigma 1. Right. So, as a whole, this is 1 plus nu divided by E into tau theta z star square. So, we can write here this is for torsion test. So, if you obtain the critical value of distortional energy from torsion test, then we have to say that 1 plus nu by 3 e into sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. This should be less than the critical value here, which is 1 plus nu divided by E into tau theta z star square. Okay. So, this is from simple torsion test. Finally, notice that this expression within the bracket, is not it a square of octahedral shear stress, right. So, this is actually proportional to tau octahedral square, and there is some factor also. Okay. So, that is why we say that the distortional energy theory and the octahedral shear stress theory, they are both related, because the expression is proportional to tau octahedral square. All right. So, this is all about the various theories of failure. Let us work out a simple example demonstrating how we can use this theory in designing a beam. Okay. So, think of a beam, a circular beam, which is subjected to both torque as well as the bending moment m. Okay. What is the state of stress corresponding to this loading? So, we have both torque and bending moment. So, due to bending moment, you can recall we only get sigma x x, is not it? And since we have a cylinder here, let us think of using cylindrical coordinate system. So, we will only have sigma z z due to bending moment, right. And how much would be sigma z z? So, that is equal to minus of bending moment m into y divided by I, okay. And z is actually the axis of cylinder. So, when we have pure bending, we only have sigma z z, and when you have only torque, we just have tau theta z, and we just found out this is equal to torque T into small r by J, correct. So, have a look at the cross section. So, suppose that is your cross section, that is your x axis, this is your y axis, and then we have z axis. So, at any point in the cross section which has coordinate small r comma theta, sigma z z becomes minus m into y, which is r sin theta, correct, and x is r cos theta divided by I. Remember that since it is m into y, so this is m x actually, the bending moment about the x axis, okay. And likewise this I here, that is the second moment of area about the x axis. So, that is I x x, Okay. And finally, tau theta z is T into little r divided by j. So, the total state of stress when both moment and torque are acting will simply be superposition of the two things. And why we can superpose? It is because we are working in linear elasticity regime. Okay. So, the sigma matrix in cylindrical coordinate system becomes, we have sigma zz, which is minus m r sin theta divided by I, and we have tau theta z, which is T little r by j, T little r by j, and rest all are 0. You can also recall that for circular cross sections, j is equal to 2 times I. So, for circular cross sections, polar moment of area j equals I x x plus I y y by perpendicular axis theorem, but here I x x will be equal to I y y. So, it becomes 2 times I x x. Okay. So, what would be the critical point in the cross section in this case? So, of course, we have to think of applying one of the theories of failure, is not it? And let us suppose I want to use maximum shear stress theory. Okay. So, let us apply max shear stress theory. So, in this case, looking at the stress matrix, we can see that R plane is already the principal axis, right, because everything is 0. So, we can draw the Mohr circle in theta z plane. So, when we do this, for theta plane sigma theta theta is 0 and tau theta z is T r by j, right. Then sigma z z is minus m r sin theta divided by I. So, the center is at the middle of the two, and therefore, this becomes the radius, right. So, with the center and radius known, we can then draw the Mohr circle. Correct. And then we can see what is the value of tau max, max shear stress. So, that is over here, and it is nothing but the radius of the circle. So, tau max equals radius of the circle, right, and that is going to be equal to square root of T r by j whole square plus m r sin theta over I divided by 2. So, it is 2 I whole square, correct, because you see this value, that is minus m r sin theta by 2 I, whereas this value, that is T r by j, and the radius is simply square root of base square plus height square, and this has to be less than the critical value tau y, let us say, okay, the critical. Now, you see each of the terms are proportional to radius. So, where exactly will this be maximum? Because that is the point where the body is going to fail first. So, that is on the outer periphery of the cross section, right, or on the lateral surface of the cylinder. So, we have to substitute small r equal to big R, and sin theta, so we should substitute equal to 1 for theta equal to 90 degree. So, that means, if we look at the cross section, these points are the points where bending stress is maximum, because here theta is equal to 90 degree and small r is equal to big R. And then the shear stress tau theta z, that is maximum everywhere on the outer periphery. So, tau theta z is max here. So, overall these are the 2 points which are the critical points, right, where the failure is going to happen first. Okay, so, we can come back here and write down the value of tau max for those 2 critical points, and this becomes square root of T big R by j whole square plus m big R by 2 I, which is j again whole square, right, and this has to be less than tau y, the critical value of max shear. Okay. Now, when we are designing this cylinder, we want to find out what should be the maximum values of torque and bending moment for which the cylinder will not fail. So, that has to satisfy this equation. So, any combination of torque and bending moment such that the left hand side is less than tau y, then it is a safe value for the applied load. If that combination becomes more than tau y, then the body is going to fail. Okay? And in reality, we always design considering some factor of safety in mind. Okay? So, suppose that the factor of safety is n, which could be 2, 3, 2.5, it is always more than 1. Okay? So, we have some factor of safety in mind. So, that means, if the body actually fails at some torque T star and we want a factor of safety n, then the operational load in the beam should be T star by n, okay, or the critical value of torque at which the beam is going to fail is actually the operational load multiplied by n. So, this means the critical value of torque and moment at failure is actually T n and m n. So, that is your T star, the value for failure, and that is your m star. So, in our formula back here, we have to substitute T star and m star, the pair for which it is going to fail. So, we come back here and then this becomes T square n square r square by j square plus m square n square r square by j square, that is less than tau y. So, which means the operational torque and moment T r by j whole square plus m r by j whole square, that should be less than the critical tau y divided by n. So, the factor of safety is reflecting on the right hand side. Okay. So, this actually limits our operational value of torque and moment, and that is obvious, right. Since we have factor of safety in mind, we never want the operational load to actually reach the critical load, all right. So, this is one example of how we can design a shaft. So, with this I am going to end the today's lecture, and in the next lecture we will work on another example, all right. Thank you.